The silhouette of a fully loaded F-16 Fighting Falcon represents more than just an aircraft. It is the physical embodiment of a revolutionary combat doctrine. A machine born from the crucible of aerial failure and forged by the immutable laws of physics. For nearly half a century, this low-cost, lightweight, single-engine fighter has dominated the skies.
Not through sheer speed or size, but through a profound understanding of energy and agility.
Its development marks a pivotal inflection point in military aviation.
A moment when the paradigm shifted from heavy, complex interceptors to nimble, pilot-centric dogfighters. The F-16 was not merely an iteration. It was a fundamental rethink of aerial warfare, driven by a classified 1966 paper filled with mathematical models.
Designed to answer a single question: how to win a close quarters dogfight.
Its design philosophy is set to be tested once more.
Against the modern counterparts of the very adversaries it was conceived to destroy.
This is the story of how a new physics-based doctrine, radical engineering, and a focus on the human element
Created one of the most ubiquitous and successful fighter planes in history.
The genesis of the F-16 is inextricably linked to the harsh lessons learned in the skies over Vietnam.
The United States entered the conflict with a fleet built on a doctrine of overwhelming technological superiority.
The standard-bearer was the F-4 Phantom II, a large, twin-engine, heavy fighter bomber.
On paper, it was a Titan. It flew at speeds exceeding Mach 2.2.
Possessed a powerful radar and carried a formidable payload of missiles. However, in the chaotic, close-range aerial battles against the Vietnamese Air Force,
the F-4's advantages often became liabilities.
Its adversary, the Soviet-made MiG-21, was its antithesis.
a small, lightweight, single-engine interceptor with thin delta wings.
The F-4 was fast, but its lack of maneuverability at lower speeds, poor pilot visibility,
and engines that billowed black smoke trails made it a conspicuous and vulnerable target.
MiG-21 pilots exploited these weaknesses with brutal efficiency, employing hit-and-run tactics.
They would fly low, under radar coverage, ambush incoming F-4s with their atoll infrared-guided missiles,
and then use their superior low-speed turning ability to escape.
The results were staggering.
Between August 1967 and February 1968, U.S. forces lost 18 aircraft while downing only 5. It's an unacceptable loss ratio for a nation accustomed to absolute air superiority. This crisis prompted the U.S. military to commission the Red Baron study.
A comprehensive investigation into the tactical and technical failures plaguing its air arms.
The report's findings were damning.
It highlighted the F-4's lack of an internal cannon for close-range engagements.
And, most critically, its deficit in maneuverability. The conclusion was clear. A new type of fighter was needed.
One that prioritized agility and energy over the brute force metrics of speed and altitude.
The intellectual architect of the F-16 was Colonel John Boyd, a brilliant and abrasive Air Force veteran.
With the help of civilian mathematician Thomas Christie, Boyd developed a new concept,
captured in a classified 1966 paper, that would fundamentally redefine fighter design.
Energy-Maneuverability theory. This paper, filled with complex graphs and equations processed by military supercomputers,
translated the abstract art of a dogfight into a quantitative science.
The theory was built on the management of an aircraft's total energy.
A combination of its kinetic energy and potential energy.
The energy differential is clear in this maneuver.
To win a dogfight, a pilot must be able to change direction more efficiently than their opponent.
Trading speed for altitude or altitude for speed. Without dissipating that energy through excessive drag.
The EM diagrams visualize this concept.
With Mach number on the x-axis and turn rate on the y-axis, the graphs defined a plane's performance envelope.
When comparing the F-16's projected performance with the F-4E's, the difference was stark. At Mach 0.4, the F-4E could achieve a maximum instantaneous turn rate of just 5 degrees per second. The F-16, in the same regime, could turn at 13 degrees per second. Even more critical was the sustained turn rate.
The maximum turn an aircraft can hold without losing speed or altitude.
The F-4's best sustained turn was 10 degrees per second at Mach 0.85. The F-16 could sustain 14.2 degrees per second at the same speed.
In practice, this meant an F-16 could complete a full 360-degree turn in 25 seconds, while an F-4 required 36 seconds.
An 11-second eternity in a life-or-death engagement.
This mathematical, physics-based doctrine became the guiding light for every subsequent design choice.
The F-16's design philosophy, as test pilot Dave Kern noted,
was a radical departure from the prevailing faster, higher mentality.
Boyd and his team recognized that real air combat rarely happened at Mach 2+. The critical arena was the transonic regime, roughly Mach 0.8 to 1.2.
The F-16's propulsion and aerodynamic systems were meticulously optimized for this specific envelope. This is most evident in its engine inlet.
Unlike the complex variable geometry inlets of the F-4 or F-15,
which were designed to manage supersonic shock waves for high-speed flight.
The F-16 features a peto inlet, a simple, fixed, flat-faced air scoop located under the fuselage.
this design is less efficient above Mach 1.2, but it is perfect for the transonic range.
And, crucially, ensures the engine is not starved of air, even during high angle of attack maneuvers.
As the aircraft's forebody helps funnel air directly into it. to prevent slow, turbulent air from entering the engine.
And causing fatigue failure from cyclical bending. And
a boundary layer diverter channel separates this dirty air and shunts it away.
the F-16's most recognizable features, however, are its wings.
The design incorporates thin, elongated wings that blend smoothly into the fuselage.
A concept known as the blended wing body.
Extending forward from the main wing are the leading edge strakes.
These strakes are a masterful piece of aerodynamic engineering.
At high angles of attack, they generate a powerful vortex of high-energy air
that flows over the wing surface, keeping the airflow attached and delaying stall.
This vertical lift allows the F-16 to remain controllable
and continue generating lift at high angles of attack far beyond conventional wings.
A critical advantage identified and refined through wind tunnel testing with NASA, who advised sharpening the leading edge to strengthen this effect.
The F-16's aerodynamic prowess is only possible because of its most groundbreaking internal innovation.
We've optimized the actuators for extreme load.
It's the flight control system.
The F-16 was the first production fighter to be intentionally designed with relaxed static stability
and managed by a quadruply redundant fly-by-wire system.
To understand this, consider a stable aircraft like the F-4 as a ball in a valley. If pushed, it naturally wants to return to its original position.
This stability, however, fights the pilot's inputs and requires energy to overcome.
The F-16 is designed like a ball balanced on top of a hill. It is inherently unstable and wants to deviate.
This instability makes the plane incredibly nimble, but it is humanly impossible to fly.
This is where the fly-by-wire system takes over.
The pilot's controls are not mechanically linked to the control surfaces.
Instead, the pilot's input is a request to a central computer,
which then commands the controlled surfaces, making thousands of micro-corrections per second.
To keep the unstable aircraft flying in the desired direction.
This system not only shed the immense weight of the F-4's complex network of cables, rods, and hydraulics,
but also unleashed the F-16's full potential.
the FBW system automatically controls the leading edge flaps and flaperons
to optimize lift and drag in any situation.
Most importantly, it acts as a guardian,
preventing the pilot from exceeding the plane's structural or aerodynamic limits.
The computer will simply not allow a maneuver that would break the airframe, limiting the pull to 9 Gs.
Or one that would cause a departure from controlled flight, limiting the angle of attack to 26 degrees.
The digital FBW system and the fighter mafia's focus on the human operator revolutionized the cockpit itself.
With the heavy mechanical linkages gone, the traditional center-mounted control stick was replaced.
With a side stick controller on the right console.
As David Kern explained, the initial design was a force-sensing stick that didn't move.
But pilots found the lack of proprioceptive feedback disorienting, leading to pilot-induced oscillations.
A small amount of movement was later added.
This side stick placement, combined with a 30-degree reclined seat, made the F-16 a pilot's plane.
The recline was not for comfort. It was a critical ergonomic advantage.
By reducing the vertical distance between the pilot's heart and brain,
it increased G tolerance by the equivalent of about 1 G.
allowing the pilot to remain conscious during the 9G turns the airframe could withstand.
A bubble canopy provided unobstructed 360-degree visibility.
A direct solution to one of the F-4's most glaring flaws.
Another lesson from the Red Baron report was the essential need for an internal cannon.
the F-16 was equipped with the General Dynamics M61 Vulcan, a 20mm rotary Gatling cannon neatly packaged inside the fuselage to minimize drag.
The weapon is a monster, firing 100 rounds per second.
From a 511-round drum that can be emptied in just over 5 seconds.
Its placement, just to the pilot's left, creates a violent and unbelievable vibration,
reinforcing the pilot's sensation of not just sitting in the jet, but wearing it.
From its precise gun sight to its integrated G-suit,
which inflates bladders to squeeze the pilot's legs during high G maneuvers.
Every aspect of the F-16 was designed to augment the pilot's ability to execute the EM doctrine.
The F-16 is a 45-year-old aircraft.
Yet it is slated to serve the U.S. Air Force until at least 2048.
Its astounding longevity is a testament to its design philosophy.
While fifth-generation aircraft like the F-35 focus on stealth technology and interconnected intelligence networks,
the fundamental physics of air combat,
the principles of energy and maneuverability that John Boyd quantified have not changed.
the F-16 remains a benchmark for raw kinematic performance.
An adaptable platform that has been continuously upgraded but never replaced.
Its combination of low cost, high performance, and versatility
has made it the backbone of air forces worldwide.
This enduring capability is now being committed to the skies over Ukraine.
The F-16 will provide a critical multi-role asset, capable of providing essential air support for ground troops pushing through entrenched defenses.
And, significantly, carrying the same cruise missiles.
that Ukrainian Su-24s have been using to strike high-value Russian assets.
Its arrival signifies a
major technological and tactical escalation in the air war.
The F-16 was born from the need to defeat Soviet-made MiGs over Vietnam.
Decades later, this machine, forged in physics and proven in combat,
will now engage the descendants of its original adversaries in a fight for another nation's freedom.
A powerful validation of its timeless design.